Okay, good afternoon. The doors are closed, so that's a sign that we will start with the afternoon session. And our first speaker will be P Cooley, and then is Tony, but Paul will give the presentation. He's Vice President of MWH, global incorporation, which are dealing or doing global life support consulting. And yeah, he will talk about rethinking the sustainable life support systems. Please, Paul.
Good afternoon. Yeah, and sort of as a disclaimer, I wanted to make the comment that my discussion today is about kind of pushing technology, but our firm doesn't sell technology as such. We don't manufacture anything. We don't build anything. We are consultants, and so we consider ourselves to be technology neutral. So what I'm trying to do and what I've been doing over the last couple of years is really trying to see where things are going in the life support business, where we need to go in order to really have a sustainable life support system. The population in the world is growing, and with increased population, there's demand on water and power, and aquariums are big consumers of water and power. The life support systems usually represent around 50% of the power consumption of the entire building. So the life support system is a big piece of it. And so to be truly sustainable, we need to always be thinking about ways that we can reduce the power consumption, reduce water consumption, and kind of push the edges of technology. And that means really kind of rethinking the typical life support system. And so what I want to talk to you today is about one little project I've been pushing forward over the last couple of years. This presentation was given at IAC, and we've moved a little bit further with it. So for the ones that were in Cape Town, it's a little bit of a repeat with a little twist at the end. For those who weren't in Cape Town, it'll be new. But the technology in the water business overall, in the water side, the wastewater side, that technology is predominantly moving towards membranes. And what are membranes? Membranes are just really micropores. It's basically producing a filter so fine that it can filter virtually anything out. And there's different types of membranes. The ones that we're mostly familiar with is RO membranes that basically can filter all the suspended material, almost all the ionic material, suspended and ionic material out of the water and produce fresh water. So there's a lot of technology being developed in that area because there's water shortages. And so there's been a lot of studies of those reverse osmosis membranes. But there's other types of membranes also that don't filter down that far. Obviously in an aquarium, we don't want to remove the salts. We don't want to remove those ionic materials. And so we're trying to get a larger particle size. This little graph shows sort of the wide range of particle removal, all the way from sand filters on the right, all the way to reverse osmosis on the left. And it basically tells you what size opening creates and blocks what material. And so, for example, you see the particle filtration on the right, sand filters, they can get down to, sand filters and other type of particle filters, can get down to 1 micron. And sand filters we use in the aquarium business, generally, 20, 25 microns. But, we can actually force them a little bit further down than that. And so where we actually trying to do, obviously, is get down below the visible range. And so that's really at the edge of the sand filter performance. And so as we looked at what kind of pushes the technology and we started looking at membranes, we said, membranes can get down to the salt, so you can remove, obviously, the suspended material, but what size membrane do we really want? And the size we're kind of focusing on, and the size that this is focusing on, is really the 0.1 or 0.01 micron range, which is the ultrafiltration range. And the advantage of the 0.01 micron range is that it knocks out all the suspended material, so it knocks out the visible range, so it produces clear water, but it also knocks out all the bacteria, so it's a sterilizer without any oxidant, and it knocks out almost all viruses. What it doesn't knock out is long chain organic compounds, so it probably doesn't knock out color. In order to knock out color, we got to take it down even further, and so it has some limitations. So what we did with Dennis Thoney from the Vancouver Aquarium is we set up a pilot plant to kind of test membranes in a real-life situation. So we picked an otter system that was an existing otter system at the aquarium. It was a small otter, sea otter system, had DE filters on it and some ozone on it, and so that was kind of the system that we chose. The existing system, is the tank, and it flows into a DE. It's a vacuum DE system, so it flows into a DE filter, pulls out of the DE filter back to the exhibit with a small ozone loop. So it's a fairly simple system, a semi-open system. And all we did was we took a small pilot system and we pumped parallel to the DE filter just to see how it was going to perform. So the pilot system, we actually tested a number of different membranes. The goal of this really wasn't to test the membranes, so we weren't trying to optimize the membrane. We were donated the membrane pilot plant by a firm called Sanitherm in Vancouver, and so they were able to fit this with a number of different types of membranes. We had a ceramic membrane, there was a plate membrane, we had a hollow fiber membrane, which is a tube membrane, and so there was a number of different tests on those different types of membranes. But we pumped the water through it, and then we measured particle counts and turbidity and coliforms, and we wanted to measure viruses, but we didn't have big enough budget to measure viruses, so we made some assumptions on viruses. We had it in an automatic backwash mode, and so what you're seeing is a 3 gallon a minute, or 0.7 cubic meter an hour filter system. And so you can see it's got a lot on it, It's a lot more than a sand filter. So what was the results? So this thing knocked out virtually all the turbidity, which is what we expected. It was a 0.01 micron membrane, a hollow fiber. It knocked out all the coliforms. I couldn't see any coliforms out of it. And because this is sea otters, you're seeing coliforms in, coliforms out. Again, we assumed it knocked out the viruses. We did particle counts, and we could see which particles it was taking out, which size particles. The particle counting wasn't really very conclusive to us. I mean, obviously it was removing particles, but the particle count technology, we didn't have a continuous measuring analyzer, and it was really not too accurate for us. And so we ended up using more accurate turbidimeters to get the ultimate result. And this graph just represents one of the runs, and the orange line is the turbidity over time. So this is a filter run time, and that orange line showing the turbidity rising from about 1 NTU up to about 4 NTUs. So it's fairly turbid water. From an aquarium standpoint, this is pretty turbid water. So we've kind of viewed it as sort of a worst case. It's a lot more than you'd ever see in a shark tank, for example, or something like that. And as the turbidity increased, then all of a sudden we had to do a backwash. Now the turbidity increase had nothing to do with this filter, of course, because this is just a small little side stream. The turbidity increase was occurring in the system, not a result of the filter. But the turbidity in and turbidity out measurements are on the upper and lower graph. And regardless of what the incoming turbidity was to the membrane, the turbidity out was essentially 0, or around 0.08, 0.05, essentially 0. Now the little yellow graph there, I just threw that in there. That's kind of what we normally see for a sand filter. So a sand filter might be able to remove 20% through the sand filter, and we're seeing essentially 100% removal. And again, associated with this was coliform removals, which was removing coliforms. So it's acting as a sterilant. So what were the problems? There were problems with the unit, obviously. This is kind of on the edge. It was backwashing very frequently. It was backwashing a lot. Boom, boom, boom. And it has an auto backwash sequence to it. It goes through a backwashing sequence. And so it was losing 45% of the water. So if the water going in, you lose 45%. So obviously that doesn't work in a true aquarium situation. So we had recovery issues. But it was definitely removing the stuff we were concerned about, which was the turbidity and the color. I mean, turbidity and the coliforms. So what was the next step then? So what we decided was, you know, in order to make this work, we gotta scale it up. And so we decided to scale it up and see if we could reduce the water usage. And there's a couple of things involved in scaling this up. One thing is that if you view this membrane system as a replacement to sand filters, it'll never replace sand filters. The reason it'll never replace sand filters is because it's way too expensive for sand filters. And so you gotta view it in a bigger sense of the whole system. And if you don't, then you'll never use membranes. And because a membrane system is much more complex than a sand filter system. So you gotta view it in its entirety. So what did we choose to go to? We decided to put it on a HIPPO system, or at least look at putting it on a HIPPO system. So you go, what? Why a HIPPO system? I mean, hippos are about as nasty as you can get. They're worse than sea otters. There's a couple of reasons. Was because we were getting into the design of this HIPPO system at the Memphis Zoo, and then membranes have actually been used on HIPPO systems before. There's an ultrafiltration membrane system on hippos at the Emmons Zoo, and it has been running there for years. And I don't know how many people have been there. I know some people, I've been talking to some people here that have been there. I've talked to the designers and the operators of it. Unfortunately, it's shut down right now because the Emmons Zoo is being rebuilt. So I wanted to go see it. But it's a very, very unusual, it's a whole presentation how they used the ultrafiltration at the Emmons Zoo. But it had been used on hippos, had been used on penguins at the Emmons Zoo. So that made me feel a little bit more comfortable. So what we did was we designed a conventional system for hippos on this project, and then we did a parallel design using membranes, just to see whether it made any sense economically. Because obviously, it's fun to use these new technologies, but if they're too expensive, and so you won't use them. And so what we had to do in order to make it work is we had to look at how does this membrane system fit into the whole system. You know, what does it take out? It's got to take out more than just the sand filters. It's got to take out other systems. It's got to reduce the size of something in order to make it work. And so we have this mathematical model that basically predicts when you put in a treatment system that treats at 20% efficiency like a sand filter and it's recirculating around, what is the water quality that will result if you take a portion of that flow and treat it to 100%? So that's what we're doing, is looking overall how the system's going to perform. And by applying that temporal model, that mathematical model to the comparison between a conventional system and the membrane system, it allows us to downsize the membrane system, theoretically. So what do? We ended up with this system, which is what we compared the conventional system to. Now hippos, again, hippos eat and excrete lots of straw, and so they're nasty little buggers. And so it flows into a screening structure. So it's got to have a screening structure to screen out that straw. And that screening structure has to be there for a sand filter, has to be there for any type of particle filtration system. So that system is in there regardless. Then we came out of the sump for the screening structure and pumped it either into sand filters or into membranes. And then because we're concerned about color, we also put it into an ozone system. So we downsized the ozone system. We were to scale the ozone system way back. So we cut the ozone, because we're getting all the water going through the membranes is sterilized. We don't need to get sterilization with as much from the ozone. We're just trying to pop the color out, get the color out. So we downsized the ozone system, and the membrane system is just a black box. So in this case, we went to GE Water. GE Water is General Electric, and it's the water division of GE Water, and they're one of the largest membrane manufacturers in the world. And they basically put some of their techie guys on it, and they came up with a design that they thought would work. And it uses a Z-weed membrane, which is a hollow fiber membrane down to 0.01 microns. So it's essentially equivalent to what we were using on the pilot plant, but it's a little bit different system. And they threw that in there, and we sized the system. So what our numbers indicated was, see, again, if we're going to put all the water through the membrane, we can't afford it. It's too much money. A membrane system for this thing would have cost probably about $2 million just for the membrane system. So what we do is we scaled it back. And so what we did was we came up with how much water can you put through it? And will you get the water quality? Remember, the clarity of the membrane system is 5 to 10 times better than the sand filters. How much benefit do you get from that? So we threw 30% through the membrane. And by shooting 30% through the membrane system, we were able to downsize the membrane system and boost the clarity. And so as a result of that, we were able to bring the project within the economics of it. So the economics paid out, meaning that the cost of this system was equivalent or better than the cost of the sand filter system. So that gives us a good feeling. Now, it wasn't good enough of a feeling, actually, because the client looked at it and they said, we are not willing to take the risk of it. So we are still designing. This job is almost in construction. So we went back to the conventional system because the client wasn't comfortable with it. They weren't comfortable with the membranes. But what we proved to ourselves is that from an economic standpoint, we believe that the membranes can reach the cost equivalent of a sand filter, conventional system. We can do that. We can design a system. The technology exists. These systems are in operation in more severe environments than what we're at. HIPPOs are pretty severe environments. So now what we're doing is looking for the next project and a client that really is willing to take a little bit of a risk, and maybe it's a smaller system than this system. But we believe that in fact, that the membrane systems push the technology. They're a little beyond what we can afford right now, but as membrane technology improves, membrane technology is dramatically improving. They're coming up with metallic membranes, titanium membranes, very cutting edge type stuff. And as that pushes forward and the cost of the membrane systems go down and there's a longer track record, more and more MNZs that are using them, we believe that they do have a place to play in the design of life support systems. So with that, I think I'm out of time.
Thanks a lot, Paul. We need to put an eye on the time, so are there any questions, one or two, to Paul? No?